Today, in this video, we will see volumetric strain of a rectangular bar. Consider this rectangular bar of length L, breadth B and thickness T. Load P is acting along the length L. Volumetric strain of a rectangular bar which is subjected to an axial load P in the direction of its length. Consider a rectangular bar of length L, breadth B and depth or thickness T which is subjected to an axial load of P in the direction of its length as shown in figure. For calculation of volumetric strain of a rectangular bar, step by step we see how to calculate volumetric strain of a rectangular bar. First, step 1. Original volume of a rectangular bar. Original volume of rectangular bar is L into B into T, length into breadth into thickness. Now, step 2. Final volume of bar. After acting this axial load P, how this bar deform this final volume of bar? Final volume of bar is L plus delta L. This L plus delta L change in length, L plus change in length multiply by breadth plus change in breadth multiply by thickness plus change in thickness. Final volume of bar is length into change in length denoted as delta L. Here not into L plus delta L. Length plus delta L, and for volume multiply breadth plus change in breadth multiply by thickness plus change in thickness. Our original volume of bar is L into B into T and final volume of bar is L plus delta L, B plus delta B, T plus delta B. Now calculate this mathematically. First solve these two brackets. L into B plus L into delta B plus delta L into B plus delta L into delta B. And remaining bracket multiply by T into delta T in this whole bracket. Now calculate this bracket, small bracket, and this square bracket. L into B into T plus L into delta B into T plus delta L into B into T plus delta L into delta B into T plus L into B into delta T. So, ignoring products of small quantity, this change in breadth multiply by change in thickness, ignore it. Why ignore it? This change in breadth is very small and change in thickness is also very small. Small quantity multiplied by small quantity is very small quantity and is equal to 0. So ignore it. This C, this delta B multiplied by delta T, delta L multiplied by delta T, delta L multiplied by delta T, and delta L multiplied by delta B by T. Ignore all this, 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 and only remaining final volume of bar is L into B into T plus L into change in breadth into thickness plus change in length into breadth into thickness plus length into breadth into change in thickness. So this is final volume of bar. Now next step 3, change in volume of a bar. For this original volume of bar, how much change in volume of a bar? Change in volume of bar is nothing but the final volume minus initial volume, and it is change in volume of a bar. So step 3, change in volume of bar is equal to final volume minus initial volume. Final volume we calculate in step 2 and initial volume we calculate in step 1. Final volume write L into B into T plus L into delta B into T plus delta L into B into T plus L into B into delta T minus initial volume that we calculate in step 1, L into B into T. See, positive L into B into T minus L into B into T is cancelled. Remaining change in volume is L into delta V into T plus delta L into B into T plus L into B into delta T. Okay. This is the change in volume of a bar. L into delta B into T plus delta L into B into T plus L into B into delta T. Now next step for volumetric strain. Volumetric strain is denoted by E and volumetric EV, and volumetric strain is nothing but the change in volume to the original volume, and our change in volume we calculate in step 3, L into delta B into T delta L into B into T L into B into delta T, and our original volume is length into breadth into thickness. Calculate it mathematically. L into delta B into T divided by L into B into T plus delta L into B into T divided by L into B into T. Volumetric strain is change in breadth to the original breadth plus change in length to the original length plus change in thickness to the original thickness. See this rectangular bar, change in length to the original length is axial strain. That means it is longitudinal strain. This delta L by L and this delta L by L means change in length to the original length. That means this longitudinal length, and it is longitudinal strain. Right. Right in step 6. Delta L by L is longitudinal strain, and change in breadth by original breadth and change in thickness by original thickness. See, this change in breadth by original breadth and change in thickness by original thickness are lateral strains. Change in breadth by original breadth or change in thickness by original thickness are lateral strains. Now In step 6, we calculate lateral strain. This is number A. 1. Number 1 equation. Volumetric strain EV equation. Now in step 7, calculate lateral strain. Lateral strain equation. For this lateral strain, first consider Poisson's ratio. Poisson's ratio is denoted by mu, and Poisson's ratio is equal to lateral strain to the longitudinal strain. And our step 7 main objective is calculate lateral strain. So lateral strain is equal to Poisson's ratio into longitudinal strain. Poisson's ratio into longitudinal strain. Poisson's ratio value minus. Why I write minus value in front of this Poisson's ratio? See, and in step lateral strain I write Poisson's ratio, and in front of this Poisson's ratio I write minus sign. See, when this axial load acting on a rectangular bar, this L longitudinal length increases and this breadth and thickness decreases. That means longitudinal length increases and breadth and thickness increases. Longitudinal length like a tensile and breadth and thickness like compression. That's why I write this minus sign in front of this mu. Opposite behavior they shown is L and BT. This is opposite behavior. That's why I write minus sign. And this longitudinal strain is change in length to the original length. See, this longitudinal strain is delta L upon L. That means delta B by B, delta T by T are the longitudinal strains, and value of this longitudinal strains are this minus mu into delta L by T. Now in step 8, put lateral strain value in equation 1. Our equation 1 is volumetric strain, and our derivation main objective is to find volumetric strain of a rectangular bar. That's why I get this one number equation. EV is equal to delta B by B. EV is equal to, directly put this lateral strain value, delta B by B is lateral strain and lateral strain value is minus mu into delta L by L, minus mu into change in length by L plus delta L by L is longitudinal strain plus delta T by T is lateral strain. Put this lateral strain value in delta T by T minus mu into delta L by L. Observe this equation, same, common it, minus mu plus 1 minus mu, EV is equal to change in length to the original length and 1 minus 2 mu. This is the volumetric strain of a rectangular bar. Volumetric strain of a rectangular bar is change in length to the original length into 1 minus 2 into Poisson's ratio mu. And also this change in length to the original length is nothing but the EV is equal to change in length to the original length is nothing but the strain, and strain is denoted by E in bracket 1 minus 2 mu, and strain is also stress upon Young's modulus. Young's modulus is stress upon strain and strain is stress upon Young's modulus. So stress upon Young's modulus. That means volumetric strain of a rectangular bar equation in terms of stress and Young's modulus, in terms of strain and in terms of change in length to the original length. How numerical? Also see this formula, EV is equal to delta V upon V. EV change in volumetric strain is equal to change in volume upon original volume. Right here EV is equal to change in volume upon original volume, and change in volume is equal to EV into V, and our EV is, see this, stress upon strain 1 minus 2 mu. This is change in volume. This is volumetric strain. This is also volumetric strain in terms of strain. So volumetric strain of a rectangular bar is change in length to the original length multiplied by 1 minus 2 mu. Our step 1 is original volume of rectangular bar L into P into T. Final volume of bar after acting this axial load P along the length, final volume of bar is L into B into T plus L into delta B into T plus delta L into B into T plus L into B into delta T. Change in volume of a bar is equal to final volume minus initial volume. L into delta B into T plus delta L into B into T plus L into B into delta T. Volumetric strain is change in volume to the original volume. Volumetric strain equation 1 we get from solving. Now volumetric strain equation is EV is equal to change in breadth to the original breadth, change in length to the original length, change in thickness to the original thickness. Delta L is longitudinal strain. This L is longitudinal strain. Why longitudinal strain? Because load P is acting along the length L and B and T are lateral strains. So that's why here this delta L by L is longitudinal strain, delta B by B and delta T by T are lateral strains. We calculate lateral strain using Poisson's ratio equation. Lateral strain to the longitudinal strain, minus sign for this compression behavior of change in thickness and change in breadth as compared to tensile change in length behavior. Now put this lateral strength values in this equation, EV equation, and we get volumetric strain. Thank you very much.